In this video, we are going to see about computer torque control. Generally, when we discuss control schemes, we will always discuss one degree of freedom schemes. That is for ease of understanding. But practically, we have n degree of freedom schemes or n degree of freedom systems. So, one degree of freedom schemes fall under SISO, single input and single output. But practically, we have multiple input and multiple output. When we have to solve problems with multiple input and multiple output, we have to analyze all the dynamics of the system. So this computed torque control makes use of the dynamic model to cancel the effect of gravity, Coriolis, centrifugal force, frictional force, inertia tensor of the manipulator. The controller discussed here employs the computed torque control law to modify the system and effectively decouple and linearize it. The nonlinear dynamic model of the n degree of freedom manipulator based on the rigid body dynamics gives the n cross 1 vector of joint torques. This is that n cross 1 vector of joint torques. So this n cross 1 vector of joint torque, we have one n cross n inertia matrix. This is the n cross n inertia matrix. And this is n cross 1 vector of centrifugal and Coriolis torques. This is the gravity torques. Again, this is n cross 1 vector. And this all adds up to the other forces which are like overall contribution of friction and other non-rigid body effects. So while designing a non-linear control system, uh, we have to understand that similar to the previous partition control schemes, here also we have partitioned the control scheme into two: a servo based portion and a model based portion. So the controller based on this complicated model provides better trajectory tracking performance than linear controllers do. The reason behind this is this controller, which which is designed now, uses computer torque control to modify the system and effectively decouple and linearize it. First, let's calculate the servo based portion to equate the system assuming unit inertia. To calculate the servo based portion, we equate the system assuming unit inertia. We have done this previously in the position control system also. Torque, the frictional force contribution, and this H factor, which is the centrifugal and Coriolis torque, these are all remain zero, uh, and the and tau dash becomes q double dot. When we calculate the error coefficient, servo errors of position and velocities are given here. This is the servo error for position, the servo error for position, this is the servo error for velocity. This relation, which has been derived, shows us output of the servo portion is the joint acceleration. Okay, so here E of t is equal to Qd of t minus Q of t is the servo error of position. This is the servo error for velocity, and respectively this Qd of t is the desired joint position, and Q of t is the actual joint position. This is desired joint velocity, this is actual joint velocity. So then we are going to calculate the error dynamics of this system. So to calculate the error dynamics of the system, let's assume that the actual acceleration is equal to desired actual acceleration plus the controller coefficients. So here KD, we know that what is KD? KD is the velocity gains of the joint acceleration. Okay, so here E of t is equal to Qd of t minus Q of t is the servo error of position. This is the servo error for velocity, and respectively this Qd of t is the desired joint position, and Q of t is the actual joint position. This is desired joint velocity, this is actual joint velocity. So then we are going to calculate the error dynamics of this system. So to calculate the error dynamics of the system, let's assume that the actual acceleration is equal to desired actual acceleration plus the controller coefficients. So here KD, we know that what is KD? KD is the uh, KD is the velocity gains of velocity gains. Here we know KD. KD is the velocity gain and KP is the positional gain. So when we calculate this acceleration error helps in deriving the error dynamics, which is given as equation number 6. So if you look at the error dynamics of this system, this is a closed loop system, and this error dynamics is specified by a second order linear error equation. And also, please understand that this equation number 6 is a vector equation and it can be decoupled on one condition if this Kp and Kd are diagonal matrices with constant gains. So why do we decouple it? Decoupling will help us in working with individual joints as we are dealing with multiple joints since we have n degrees of freedom systems. And if we write the error equation on a joint by joint basis, we will get for a ith joint this error equation. The same error equation 6 can be rewritten as the error equation 7. And we know that KDI is the velocity gain of joint I and KPI is the positional gain of joint I. We have already seen that for a robot manipulator, the joint should be critically damped. Hence, this condition must be satisfied. This condition must be satisfied where Kd, that is the velocity gain, is twice the square root of positional gain. If we maintain this, our manipulator or the joint would be critically damped. There are few limitations in this system. Limitation number one, the system is complex. So we don't assume everything in this system. We take everything in this system into consideration. So things are complex. So any error which occur on any of the parameters can affect the system. Point number two, or limitation number two, is this is computationally expensive. We need we need computers which are very fast, and for slower computers it takes time for calculation. Okay, so to avoid this we can follow various methods. This can be force control, discrete time control, impedance control, and robust controls. This will help to reduce the errors occurred in this system. This is the block diagram for a nonlinear controller based on the computer torque control law. Here we have two portions, a servo portion and a model based portion. The output from servo portion is tau dash of s, and outputs from the model based portion is the position as well as velocity. This position as well as velocity fit to this block, which adds to the controller here, which is controlling the plant, which is the manipulator. And as usual, we have three inputs to the servo portion. One is the desired position, desired velocity, and desired acceleration. The errors, the servo errors are this. The servo errors for the position is this, which is fed with the position gains, and the servo errors for the velocity are fed with the velocity gains, which adds to the output of the servo portion, which is again provided to the model based portion.